Hello friends, welcome to our channel. In previous video we discussed about open set and open spheres. In today's video we will discuss interior of the set and some result based on interior of the set. Theorem: the interior set of a subset of a metric space is the largest open set contained in the set A. Proof: in this theorem we have to prove three results. The first, we will prove the interior of any subset of a metric space is open set. Second, we prove that interior of the set is a subset of the given set. And the third and last, we have to prove that interior of the set is the largest open subset. So we will discuss one by one. Let XD be any metric space. Suppose A be the subset of X and A interior is the interior of the subset A. First we prove A interior is open subset. If A interior is equal to 5, then there is nothing to prove because empty set is always open set. That is, A interior is open. Suppose A interior does not equal to 5. So there exists X belongs to A interior. Now we have to prove that A interior is neighborhood of X as X is belongs to A interior, that is X is interior point of the subset A, that is A is neighborhood of X. So there exists R greater than 0 such that sphere centered on X with radius R is contained in A. We prove that SRX is contained in A interior. Let A is belongs to SRX. We know that every open sphere is an open set. This implies SRX is an open set. This implies SRX is neighborhood of all its points. This implies SRX is neighborhood of A. So there exists R1 greater than 0 such that sphere centered on A with radius R1 is contained in SRX. This implies SR1A contained in SRX contained in A. This implies A belongs to SR1A contained in capital A. This implies capital A is a neighborhood of small a. This implies capital A is an interior point of capital A. This implies A belongs to A interior. A belongs to A interior, but A is an arbitrary point of SRX. This implies SRX is contained in A interior. So A interior is neighborhood of X, but X is arbitrary point of A interior. This implies A interior is neighborhood of all its points. Thus, A interior is an open set. Now we have to prove that A interior is contained in A and A interior is the largest open set. By definition, of interior of the set, we have A interior is equal to x belongs to A such that sphere centered on x with radius r is contained in A. This implies A interior is subset of A, that is A interior is contained in A. Now we have to prove that A interior is the largest open subset of A. Suppose B be the another open subset of capital A. We have to prove that B is contained in A interior. Let Y is belongs to B. As B is open subset of A, this implies B is neighborhood of all its points. This implies B is neighborhood of Y. So there exists r greater than 0 such that sphere centered on Y with radius r is contained in B. This implies sphere centered on Y with radius r is contained in B and B is contained in A. This implies Y is belongs to sphere centered on Y with radius r contained in A. This implies A is neighborhood of Y. This implies Y is an interior point of A. This implies Y is belongs to A interior, but Y is an arbitrary point of B. This implies B is contained in A interior. B is any open subset of A. This implies A interior is the largest open subset of A. Thus, A interior is largest open subset of A contained in A. Next theorem. Let XD be a metric space and A be any subset of capital X, then A is open if and only if A is equal to A interior. Proof: let XD be any metric space and A be the subset of X. Suppose A is open, we have to prove that A is equal to A interior. By definition of interior of the set, we have A interior is equal to X belongs to A such that sphere centered on X with radius R is contained in A. This implies A interior is contained in A. That is, A interior is always subset of A. Put it equation number 1. Again, it is given that A is open, let X is belongs to A. This implies A is neighborhood of X This implies there exists R greater than 0 such that sphere centered on X with radius R is contained in A. This implies X is belongs to SRX contained in A. This implies X is an interior point of A, that is X is belongs to A interior, but X is an arbitrary point of A. This implies A is contained in A interior. Equation number 2. From equation 1 and 2, we have A is equal to A interior. Hence, if A is open, then A is equal to A interior. Conversely, suppose that A is equal to A interior, we have to prove that A is open, that is A is neighborhood of all its points. We know that A interior is the largest open subset of A contained in A, that is A interior is open. This implies A interior is equal to A is also open. Hence, if A is equal to A interior, then A is open. Next theorem. Let A be a subset of a metric space XD, then A interior is the union of all open sets contained in capital A. A interior is the largest open set, and we have to prove that A interior is the union of all open sets contained in A. Proof. Let XD be any metric space and A be the subset of X. Let G lambda belongs to indexing set, be an arbitrary collection of open sets contained in A. We have to prove that union lambda belongs to indexing set G lambda is equal to A interior. Suppose union lambda belongs to indexing set G lambda is equal to G. As G lambda belongs to indexing set is open, this implies G is also open, because arbitrary union of open sets is open. Also, G lambda is contained in A for every lambda is belongs to indexing set. This implies union G lambda, lambda belongs to indexing set, is contained in A. That is, G is equal to union lambda belongs to indexing set. G lambda is a subset of A, which is open. We know that A interior is the largest open subset of A contained in A. This implies G is equal to union lambda belongs to indexing set. G lambda is contained in A interior. Put it equation number 1. Next, let X is belongs to A interior. So there exists R greater than 0 such that sphere centered on X with radius R is contained in A. We know that every open sphere is an open set. This implies sphere centered on X with radius R is open subset of capital A, but G is equal to union lambda belongs to indexing set. G lambda is the collection of all open subsets of A. This implies sphere centered at X with radius R is contained in G. This implies X belongs to sphere centered on X with radius R is contained in G. This implies X belongs to G, but X is an arbitrary point of A interior. This implies A interior is contained in G. Equation number 2. From equation 1 and 2, we have A interior is equal to G is equal to union lambda belongs to indexing set G lambda. That is, A interior is the union of all open subsets of A. It is sufficient for today. In the next video, we will discuss about the closed set in a metric space. So keep in touch, watch our videos and subscribe our channel for more videos on these topics. Thanks to all. Have a nice day. Bye bye.